These are the characteristics. We have learned some characteristics last week about how to calculate the torque, of the induction motor. But today we'll study some more characteristic curves. For example, see here, there are several curves. First, the speed characteristic curve. Yes, is the n. N in the speed, so is this curve. This curve of the induction machine. So the x-axis is output power. So the larger the output power, the lower the speed. But it's nearly a straight line. It's nearly a straight line. Just a little downward. And the second line is the static current. Just here, the I1. The I1. This curve. I1. If the output power increases, so we know the input power should increase also. So the current of state will increase also. So this is I1. Also, there's no R2, but we should know the R2, the rotor current will also increase. So this is the two curves. Let's see, and also the third power function. Is the cosine phi 1. Cosine phi 1. It's so many curves. Cosine phi 1 is this one. It has a maximum value about here. And if the output power is nearly the rated power, so the cosine phi will decrease with the cosine phi 1. And also the fourth is the torque. The torque. We have studied how to calculate the torque of the induction machine last week. Here, just give the curves. The torque is here is the PE. So it's the electromagnetic torque. And also the last is the efficiency curve. Maybe this one. So it's nearly the power factor. This one is the efficiency. So these are the five curves of induction machine. The characteristic. The most important is the torque, the electromagnetic torque. The number 4, the torque is the most important. We will use this curve and have some calculations. typical torque. So the x axis is speed, and the y axis is torque. So it's a little different from this. A little different from this. The x-axis is the output power. But if we talk about the torque singularly, we just use as torque speed, speed torque, torque speed curve. This is generally used. It's a plot of induction motor torque, Vs speed. And the speed is from 0 to the rated speed. Also, it's the synchronous speed. If for this 1,800 maybe 4 pulse, and the frequency is 60 hertz. So we should say the three items. First is starting torque. Here, the starting torque, 100, and the pull out torque. So also is the maximum. It's the maximum torque. The pull out torque, and the operating range. The motor usually works at this position. So the speed, the rotor speed, is nearly its synchronous speed. So it works at this position. So the slip is about 5% slip here. This is the speed of the top speed characteristic. And also we see this graph is also the speed, the torque Vs speed, but the axis, so here is omega, this one is A. So we see there are some points, patient. We should know some 6 or 5. Should know some points that first the start method of the induction machine. How to start an induction machine. So it can be used as a DOL start. DOL start is just the direct online starter. So just connect the terminals of the motor to the source, to the power source. So it can be started use this method. But if we use this method, we'll see this one. The IS, the state current, will be very large. So when we start induction motor, use the DOL start, direct online. So the current will 5 to 8, or sometimes to 10 times of the rate current. So it's a large current. It will resistance to the power.
This
so
make a large gate.
So especially if the machine is high
High
power, then and also we know this the start torque is less than the pull out torque. But if we use some speed control method, just and use the resistance to adjust the speed, so the curve will vary, will change. So the pull out torque and the starting torque, the relationships between them will change too. Maybe another, just like this curve, maybe the curve between them.
If starting torque is fixed.
Yes.
When you
it can change. Change, especially for use one rotor. We use resistance,
series of
resistance, so we can adjust the starting torque. We can adjust the starting torque.
So if I use this resistance with this rotor stator, so should I have to use this series or shunt?
The sleeve. We can adjust. We can increase this torque if we want a larger starting torque. We can just connect it as a rotor to the resistance. We can increase the torque, the starting torque, just like this curve, the red curve.
So I can connect this resistance. For this is series resistance or shunt?
Series to the rotor. One rotor induction motor. Series. We will talk this in the next in the other slides. How to control the torque and how to control the speed. Maybe tomorrow. Tomorrow we'll talk about this. And here the maximum torque is about 2 or 3 times the rate torque. Maybe it can be equal if you see this red line. The maximum torque is also the starting torque. If this is red curve, here is the starting torque, and here is also the pull out torque. So we should understand this sentence. Pull out torque usually 2 or 3 so it's sometimes it's not this. Maybe there can be equal. And the last one. We generally want start a motor more quickly, so we need a larger starting torque. But a larger starting torque will induce a larger step current. But if the time is short, so we can endure them. So we hope the starting time, the shorter the better. So this is some points about the torque speed curve. So let's see some example. This is a wound rotor.
Three.
This is a wound rotor induction motor. So this is the external resistance. We change the resistance. The external resistance. We change the value, and we'll change the curve. We'll change the torque speed curve. Different resistances value R1, R2, R3, R4, R5. R1 is less, small, is more small, and R5 is the largest. So different resistances corresponding to different curves. Different curves will have different starting torque. Different starting torque. If we use a large resistance, this one is large, so we have a large starting torque. But if you use this curve, the 5, so it will have some losses on the resistance. So the efficiency of the motor, will be influenced. Will have low efficiency.
Sir, this is the YY connection.
Okay, it's just during the starting, but after starting, we have got if the speed is high. After starting, the speed is high. We'll change the resistance from 5 to 1. So it will decrease the losses and increase the efficiency of the motor.
Sir, this is stator, this is rotor, and this is the YY connection.
Oh, not this.
This is the resistor. This is the Y connection, yeah? This is Y.
This is the stator.
Delta.
Stator.
This is
not connected here. So maybe this graph is some mistake. No, not connected together. Not together.
Oh.
So it's a single. It's a
Single line.
It's a single circuit. So they are not connected here. They're not connected here.
This 3 brass and this one. This 3 brass.
Rotor just to the. So if this is there's I see.
This is the Y, sir.
No stator. No stator.
Just rotor.
No stator. Just a rotor. Just a rotor.
And this 3 brass.
No stator winding. There's no stator winding in this graph. So this is the rotor. Rotor winding. So just this is a slip ring. The three slip ring.
This is the Y connection, yeah? This 3 brass is Y connection.
Y connection.
Yeah.
So connection to the resistance.
1 ring, 2 ring.
So here, the connection here. So this is rotor winding. So it doesn't join the stator winding. No stator winding here. So it's not joining on this graph. So it's okay. So just a rotor. So this is wound rotor. This is a wound rotor induction machine. Not just and here. So this is a slip ring. So 3 slip rings. This is a slip ring. And this is winding, the rotor winding. So is this corresponding to this? So just connect to the 3 rings. Just connect to 3 rings. this equivalent circuit. So we have studied this last week and started some calculation on how to calculate the power and the losses. Use this equation. But today we use this circuit just for the torque calculation. So we can see these equations is similar to last week's equations, but just some is different. So here use the VTH is use 70 equivalent circuit. So so here use presented by VTH 70
notice.
Just we have learned how to calculate these values and the impedance. So the source. Let's have a review. Resource is include the R70 the inductance of the so it's equivalent and X2 is the rotor inductance. So you can calculate this. So if we want to have the maximum torque, so the R2 over S is equal to the sum of this impedance. So because they are vectors, so use this equation, the square. So R is 70 square. So plus the two inductance square. So when this equation so this time we'll have the maximum torque. So we can from this equation we can calculate the corresponding speed. The corresponding speed. So it's we use the max to designate it as max. We can calculate the max speed. The max speed is here. The speed. We can calculate the speed at this point. And the torque. This is the so this use the torque, but last week T is T. It's down. So it's a little different. But the equation is the same. Just with this equation, it's can see here. So the general.
This is our rotor resistance, yeah?
R2 over S.
Yeah.
R2 over S.
R2 is our rotor resistance, or R2 over S.
R2 over S.
But how do we get this way?
So here, this is R2 over S.
No, sir. So why this is the not X2 over X? This inductance. If I write total resistance R2 over X, so rotor inductance. Why not this is the X2 over X? I mean if this is R2 over X, why not this is X2 over X?
Equivalent. So because we get the maximum power is a part of the source. It's a part of the source. So it's use the sampling the sampling equivalent zero. It's a sampling zero. So it's here. It's here equal to the sum of the three ones. So it's the circuit equivalent circuit is the maximum zero. It's maximum zero. You can see some the circuit book. So use the equations. We can calculate the sleep, the maximum the sleep and the torque. So we say the S max is proportional to the R2 is proportional to the rotary resistance, and inversely proportional to the sum of all the state and rotor leakage reactance. We see the slip is independent of the voltage. So you didn't see voltage in this equation. There's no voltage here, so it's independent of the voltage. It's just a function of the R2 and the leakage inductance. So let's see, use a simple example. So it's twofold.
Induction motor supply.
50 Hz induction motor, 15 kilowatt, and also the rotor speed is
Motor slip.
2950, nearly 3000. So what's the motor speed? Slip we can easy to calculate because we know the
Speed
rotor speed
and motor
and know
supply.
the synchronous speed.
Twofold.
So A is simple. And B, so to calculate the induced torque, if the motor on this condition, so this can also calculate because we have the equations. So and C, the operating speed, if the torque is double, so we also calculate it if the torque is double. And for the power, also C and D is the same. C and D is similar. So let's see. So let's see. So we can easy to calculate the synchronous speed and the slip. Easy. Only slip is small, 1.6, and the torque use the power over divided by the omega, the speed. So we know it's 15 kilowatt. Let's use this equation. Easy to calculate the torque. If the torque is doubled, so this one, torque is doubled. What to say the S?
Slip.
also the power. Power is equal to the torque times the speed. So this simple example. Okay. Okay, we have learned the operation characteristics. There are some basic calculations, just like we have learned in the equivalent circuit, the power and torque equation. In these two parts, we have the similar calculations. And next is different, but have some relationship with this. It's the starting and the speed control. First, we set the starting. So how to start induction motor. Okay. So we have just set the method of DOL direct online. Just connect the terminals of the motor to the power source. So it's the method of DOL. So it usually used with small motors because small motors, so the current, static current will be small too. So it will not influence the power source. But large motors, the current will be larger. The current will be large. It will destroy the power source. So we need some method to start the large motors. You have several methods. We'll learn it in the next slides. And also the starting arrangement based on these two is depend on the supply, and depend on the load. And this the start torque. It should not be zero. If the start torque is too low, it can't overcome the friction. So we should have a number of the start torque, and also the start torque can't be too large. Or else it will destroy the power source or the wires. So let's see the system in detail. So we say this equation is a slip. When we want to start induction machine, so the speed is 0. So the slip is equal to 1. And this time we look these two equations. So it's the cousin and the torque expressions. We know the R2 is the rotor resistance. It's usually very small, and R1 is the stator resistance. It's small too. So both the resistance is small, and we'll get a larger current. We call it the high starting current, because in the general equation, so here is R2 over S. It's R2 over S, but the S is equal to what? So here is R2. So the value is small, and the current is high. And also we see the torque equation. It's similar. So the R1 plus R2. So the resistance is small. Also, also here, but we also have the R2 here. So the resulting is we can calculate it on the code. So the torque is low. The torque is low. If we have the big low torque, it can't overcome the friction. It can't overcome friction, so it will not start the induction machine. So we want to have high starting torque but lower starting current, and we hope that situation. But the real is this is the real situation. So we have to make some methods to overcome this problem. So let's see this. This is the torque speed. It's the torque speed curve. We have just studied this curve. So the three curves are for different voltages. So this method, starting method, we call the reducing voltage. Reducing voltage starting method. You see here. This equation, why use reducing voltage? Because we see here, if the voltage is the stator voltage, if the voltage is low, so the starting current will be low, and also here. So the first method we can imagine is that to reduce the voltage, but you know, if we reduce the voltage, although the current is low, but the torque will low also. So in this curve, we use the lower voltage. We can get the lower current, but the start torque will low too. So this is the drawback, disadvantages of this method. Just the equation is here. So the curve is joined by these two equations. So the torque is proportional to the square voltage, square of the voltage. So we can conclude that. So this method, the advantage is that the current is reduced. The current is reduced. The current here, the low voltage, the low current. So this is good. This is good because we have low starting current. So this is good, but the torque, the starting torque is not very good. It's not very good. So it can't start. A heavy load. If we have a heavy load, so you can't start the motor. And also the maximum torque is reduced. The maximum is reduced. So the acceleration is low. So you can't have reach to the speed in a short time. Can't reach the speed in a short time. So this is not good. Not good. But we see the three curves. The maximum speed is set. Or at this sleep, the same sleep, it will the three curves reach the maximum torque. But the value of the maximum torque is different. So it's this method of reducing voltage method is not a very good method. It's not a very good method. But in some small load torques, we can use it. If the load torque is small, we can use this method because this method is simple. Is a simple method. This is the torque equation. Okay, let's take a break. Then we'll talk about this. It will start at lower voltage, but after the speed up, we should connect close to the rod start, and the start contactor is open. So then direct connect the source from here to this is closed. So here to the terminal. So after starting the motor, direct connect the source to the motor. So it has two. In this situation, we have two voltage levels. One is high when the R is closed, while another is low voltage when the S is closed. So it only have two voltage values. Let's see another method. Also can reduce the start voltage. We call this the name is starting. Use this circuit. It has six terminals. Six terminals of the stat windings. So first, we use the star connection. So the switch is connected to the right side, and this also right side to connect to this terminal. So in this time it's a star connection. This is the neutral point. So the current from here is line here. Also the other phase and the C phase. So it's a star connection. In star connection, so the voltage is the phase voltage. So is the phase voltage from the line to the neutral. Line to the neutral is the phase voltage. For example, is 220 volt. But after we are starting the motor, we just connect the switch to 1, to 2, to here. The switch to 2. Switch to 2, we see that it's a direct connection. So here, from here, it's a start to B and to C, and also back to F. So it's a direct connection. The voltage between two terminals are the same as the line voltage. For example, is 380
line to line.
So it's the line voltage. In this situation,
for this connection, S is source and delta is load. This load.
No, this is only the stator. It's only the stator winding, no load winding.
This only
only the stator. So it's this is the terminal of the stator. So it's the stator winding. To generate the rotating flux. It's just the stator winding. So the road winding not in this graph. So generally it's a squirrel cage. It's a squirrel cage motor. We can't access the rotor circuit. Generally, this method, this startup method, is generally used to the squirrel cage motor. But the last one, this one, we see that this also the state. It's also the state winding. So also we didn't see the rotor circuit. It's also a squirrel cage. But we can also use this for wound rotor motor. Just short connected the rotor short connected. So in the method 2, start method, we have two levels, two voltage levels. One is the phase voltage, and another is the line to line voltage. So it's the method 2. And also we have the third method. This is a lecture note. It's named solid state voltage. Solid state voltage control. It's presented by this. Is a side resistor. So this method is better because the voltages the voltages from the source to the motor, the voltages can be adjusted gradually from 0 to rated voltage.